violet spectrometer or spectrograph on LRO, and it has a passband that goes down to 520 angstroms, so we can see helium at 584. And it is a 2 degree or 0.2 degree by 6 degree slit that is divided into 0.2 degrees spatial pixels. This 6 degrees is divided up into spatial pixels. And as the LRO goes along the moon, it maps out the other direction. So as you've seen in some talks earlier, one of the goals of LAMP, which was one of the secondary goals in the main mission, or the ESMD mission, but one of the prime goals in the science mission is to look at the atmosphere of the moon. And in order to see the atmosphere, we see it by resonant scattering. So the atmosphere that we're looking at has to be illuminated by sunlight. But if LAMP is looking at the sun or at the bright surface of the moon, it's hard to see the atmosphere. So we need to be looking out over dark sky or the dark surface. So there are two modes. One is our nominal operating mode is looking nadir here. So it's looking at the dark surface here on the night side, but looking through illuminated atmosphere. Or limb viewing mode, we don't get to do that as often, but that gives us a much longer path length through the illuminated atmosphere, and so we get better signal to noise. Now, when LRO transitioned into the frozen orbit, it's made the conditions for looking at the atmosphere better for us because the frozen orbit has a periapsis around 30 kilometers down here and an apoapsis about 200 kilometers. And so there's a lot more illuminated atmosphere to look through at apoapsis. And regardless of if we were at the 50-kilometer orbit or the frozen orbit, this is much more amenable to studying the atmosphere when beta is near 90 because you have this whole time when you're on the night side where you're looking through illuminated atmosphere and looking down at the dark surface as opposed to when you go further into the night side, you actually pass into the shadow and you're not looking through illuminated atmosphere except at the poles. So to understand our data, we measure counts at helium 584, and those counts are coming from scattered sunlight. So we need to know what the solar flux was. We get those data from EVE, the EVE instrument on SDO, and this shows what the G factor is for helium derived from SDO as a function of time in the time period that we're going to look at today, which is from late December and January, late December 2011 and January 2012. And then we also calibrated the instrument at 584 by using the background helium, sky background helium. And Wayne Pryor has done or provided models for us of what the helium map looks like and how that evolves over time. And so this shows an observation where we're looking out here and we're looking a little bit on the dark moon and this out into the background in this densest or brightest region. And this red spectrum is from the dark part, and the black spectrum is from the background, and you can subtract out the dark to get the helium signal here. Okay, wow, all right, that's hard to see. But what this is showing is what our Nader observations look like, we have the orbit altitude here. So here we're starting on the day side, going up at the North Pole at apoapsis, and then on the night side down here, and then back out on the day side. And this line down here shows what the shadow height is. So here we're on the day side, we can see all the way down to the surface. This altitude here is where the shadow, or the atmosphere under here is in shadow. So this atmosphere here is what we can see because we're looking down at dark surface of the moon, and this part is illuminated. So that was one of our days, December 30th. And then as LRO's orbit progressed further into the night side, you can see the shadow height comes up quite a bit. And so now we're only looking through illuminated atmosphere over the North Pole and the South Pole there, just a little bit. So what we do is we compare the observation, or hold on, back up for a second. So then what we can do is we can take the spectra when we're looking at the dark surface and compare it to over here where we're looking through illuminated atmosphere. This dark surface spectrum is the red one, and the illuminated one over here is the black one. And subtract out what our helium signal is. And so we add up our counts and we compare it to the Chamberlain model, where we keep temperature fixed at 120 Kelvin, and we integrate between the shadow height and the LRO altitude, and we scale this whole curve this way to match the data, and then we trace it back down to what the density is at the surface. And so all the values that I'm going to show you from now on are this density at the surface. So it's basically how far we have to move this curve to get the integrated counts here to match the data. And so this shows the results from 2 different days. And what we've done is we've taken the 12 orbits from one day that are basically repeating over the same local time and this, same altitude at the same latitude, and added up the signal from those 12 orbits. So each point here is like 12 points from the different times in the day when we were 300 or 3,000 seconds after passing the equator. So this is, but it's always the same position. This is always the North Pole and South Pole down here, and the night side here. And so keeping the temperature constant in the model at 120 Kelvin and the density at the surface constant at 1.82 times 10 to the 4 cc, or per cc, we fit this line here to the data. And so you can see that as LRO is going to different latitudes at the same position on the night side, same local time, the density doesn't change very much. And then one of the later orbits over here, same thing, fit the model 120 Kelvin, but this time we used a different density at the surface. But you get a very nice fit throughout the whole entire night side. So density is not changing as a function of latitude or helium in the lunar night side. So now these are what the fitted surface density values are as a function of time. We have time down here, and then the surface density values for those day-by-day averages. And, you know, it looks kind of funny. There's this big dropout here, but that dropout is from when the Earth goes into the, or the Moon goes into the Earth's magnetotail. And we picked out the times that the Earth went into the magnetotail by looking at Artemis data. So that's nice that those data are available to give us the context clues that we need to understand what's happening on the Moon. You may also notice that the density is much lower here than it is up here. Well, actually, first of all, so the drop from going into the magnetotail to when the Moon actually starts leaving the magnetotail is about 35% of that value. So thanks. It's quite a substantial drop in the helium exosphere of the Moon because the source is turned off. You don't have that solar wind providing the helium. But then, so before or when the Moon leaves the magnetotail, it goes back up in just a few days, and it proceeds further up. And that is just a matter of the LRO's orbit has progressed further into the night side, so the densities are higher at longitudes that are further into the night side. Now, we've modeled these data with a time-dependent Monte Carlo model to try to understand how the source rate is affecting the helium measurements. And this is important because the helium source is on the day side and the measurements are on the night side. So there is a transport process involved, so you have to account for that somehow. So this line here shows using a constant source rate, except for the times when we're in the magnetotail, what the helium density would be. And you can see it's morphologically gets the longitudinal differences and it gets the magnetotail dropout. There are variations from this line which may be due to just variations in the day-to-day solar wind flux. Now, these data were mostly from the terminator on the dawn side, just before dawn. There are some observations that we've just done for the terminator on the dusk side, and there is an asymmetry there, and look to the future to see those results. And that asymmetry was seen by LACE. So, in summary, we've observed the lunar helium exosphere with LAMP, and this is a really neat observing geometry where beta is near 90, and we can do observations throughout the entire night side path. We find that there's little or no variation in the helium density with latitude, but there is a variation with longitude, which is consistent with what LACE saw, the longitude measurements, that is. And there's a decrease to about 35% of nominal density when the Moon passes through the Earth's magnetotail, and possibly day-to-day variations reflecting the solar wind variations. And Paul submitted this paper to Icarus. So look for that in the future. Thanks.
Time for one quick question.